Okay, so let us have this example. So this is a similar problem. A cable carrying a series of pointed loads. However, it so happened that this problem gives the sag distance wherein this D is 15 meters from the lowest point and vertically located on the projection of this chord connecting points A and B. So that is 15 meters. So you know the approach. We have introduced the step on how to do this. First, we will have a fictitious reaction here. We have RAY and this as RBY. Then the two horizontal reaction both supports. So next is we place all the vertical reactions on a beam, and of course we establish the shear and moment diagram. Okay, so we note the distances as well as the points, and then we take moments at A and B to solve for your reactions. And of course it is obvious that RAY and RBY shall be equal because of symmetry. So you just have to share or absorb the loadings, which is equal to 400 plus 200 plus 200, that is 800. So the reactions RAY and RBY is the half of that. So both will have 400 each. And then we establish the shear diagram. We go upwards 400. No loading, so it remains to be 400 until the 200 will push it down by 200 units, so it will just yield to 200 also. No loading remains to be 200, and then 400 will push it down to negative 200 until this 200 will push it further by 200 downwards, 200 units. So that this is remain to be negative 400 until this will push it back to 0. Okay, so this is the shear diagram. And then for the moment diagram, we have first we compute the 400 by 15, and I think this shall equate to 6,000, and then add further 200 by 15 positive area. We have the 9,000 value, and this will just have a symmetrical configuration. So this is now our moment diagram. Okay, so by the way, let me correct this depth here, or sag depth, that should be located at the maximum moment, which is 9,000. Actually it is on the 400 kilonewton loading. So let me just transfer that. Okay, so that is suppose is the location of the 15 meters. Okay, so by this we have learned that the relationship of 400, the sag depth, and 9,000 is this one. HD is equal to M. So substituting the value, we have H times 15 is equal to 9,000. So we find H to be equal to 600 kilonewton, wherein this is the value of horizontal reactions at A and B. Okay, so knowing our horizontal reactions at A and B, we can just take summation moments at A and then solve for B. Okay, so we have summation moments at B is equal to 0. We have negative 200, that is actually counterclockwise, times its moment arm 15. So we have also this one, the 400 times its moment arm, which is 30, and another 200 with 45 moment arm from B. So we deduct the counterclockwise H here times the moment arm equivalent to 24. Okay, and then finally RAY would have a clockwise rotation times 60. Okay, so we have that one would be equal to 0. So RAY is 640 kilonewton. So note that this is now the real value of RAY, because a while ago RAY was only a fictitious value just to apply the ruling of the relationship between H, D, and the maximum moment. Okay, so we also get our the other reaction. Actually, we can just use summation forces vertical, or you might want to use this one and then just check it by your summation forces vertical. So anyway, we'll take moments at A to solve for RBY also. So we have 200 times 15 plus 400 times 30 plus the other 200 with the moment arm of 45 minus RBY times 60. Okay, what else? Minus this H times 24, and this shall equate to 0. So by the way, this is actually 600 like this a while ago. Okay, so we can now solve for RBY. We have RBY is equal to 160. So if we are going to check our reaction using the equilibrium equation along the vertical, we just have to check this. Okay, so all in all we have 200 plus 400 plus 200, that is going downwards 800. So that will be denoted by negative. We add this upwards 640 and this 160, so it will really yield to 0. Okay, it will really yield to 0. So we are now assured with our reaction. Okay, so we'll place our computed reactions on this. H actually is equal to 600, so we will place it here: 600, 640, 160, and 600. So if these are the reactions, we can actually resolve if we are concerned with this the tension of this cable, the adjacent cable on this side or within this side. Then eventually we can compute for the other tensile at the cable on any sections. Of course, we start with this one. Okay, so we will get its joint. So at joint A, so what is in joint A is the two reaction, vertical and horizontal, and remember that this shall yield to RA as its resultant, which is actually collinear to your cable here. So if I'm going to label this as 1, this is T1. So we can say that RA is equal to T1 equal to square root of 600 squared plus 640 squared. So we'll have 877.27 kilonewtons. Okay, so we can do the same in your RD. Okay, so the point here. Say if this is D and this cable is 2, your result here shall be parallel to the cable 2, and this is actually RD as a result. So similarly, in similar way, we can compute that one. We'll have RD is equal to tension at 2. So this is a parallel T2 here, which is equal to the square root of 600 squared plus 160 squared. So by this, we can solve now for tension at 2, which will be equal to 620.97 kilonewtons. So this is our tensile at 2. So that's it for this problem. So the variation is that this problem contains the sag distance on the point where the maximum moment occurs. Okay, that is in point C, actually on the 400 kilonewton. So that's it for this problem. So let us try another one. Okay, so let us consider this one. So this is a parabolic curve that is carrying a surcharge of 5 kilonewton per meter. It so happened that the sag, or the lowest point, is within the symmetry of 60 meters. So the sag distance is given, where the distance of the lowest point to the point of intersection of the chord connecting A and B, and that is equal to 5. So basically, we are going to separate our free body diagram, or considering the left portion and the right portion if you want. So I'll just consider the right portion anyway, or the left portion anyway. They have the same reaction along the horizontal line but different on its vertical axis along A and B. Okay, so singling out the left portion, we are on the lowest point here, so therefore the slope is 0. So your tension at this point is your horizontal H, and we will just resolve this. So remember that this is a half, okay, half of 60, and we note that these are 15 meters, so that the result is 5 by 30. So this is 150. So we note the distance of H to H from A is supposedly equal to 5 meters, though the projection of 5 should be here. Okay, should be here. So anyway, the problem itself should tell that it shouldn't be symmetrical because of the gap between A and B. So anyway, this is a problem on the book. We still need to solve it and then assume values here. So this is supposedly 5, so that we take moments at A. Okay, we have negative 150 by 15 plus H times 5 is equal to 0. So we can now solve for H, which should be equal to 450 kilonewton. Okay, so if this is known, we just place it on the whole structure and then solve for RAY and RBY. So this time we are going to take moments. So taking moments at A, we would want to, of course, resolve this. We have a resultant for that distributed load equivalent to 300. Okay, so of course that is 60 is just bisected there. So we have 300 by 30 plus 450 times moment arm. I think we are lacking given here, so maybe place the right given. So from the problem, this should be 10 meters. So if that is 10 meters, okay, we just place it here. And then we have RBY that would yield a counterclockwise moment times its moment arm equivalent to 60. And that would equate to 0. So we calculate RBY. So RBY will yield to 225 kilonewton. And then we would like to find the other reaction. So again, we take moments at the other support. we have summation moments at B is equal to 0. We have negative 30 times 300 plus 450 times 10 plus RAY times 60 is equal to 0. So calculating for RAY should be equal to 75 kilonewton. So now that we have this reaction, let us check. Actually, RAY and RBY will be your vertical upwards. So if we are going to add that one, it will yield to 300 upwards. Well, in fact, we have here a downward 300, so it is obvious that we have satisfied the vertical equilibrium, okay, with that. And so finally, if we will be concerned with your tensile, okay, the tensile here, okay, say this is RB, and the tensile on the other side, which is collinear to your cable, this is say this is RE. We'll just have to apply our principle on Pythagorean theorem. We'll just get the components squared, the sum of it, and then square root. We have RE equal to 406.97 kilonewton. And as for RB, we do the same or similar manner. We have square root of the horizontal one, okay, that is 450 squared plus RBY, which is this one, 225 squared. So calculating that, we have equivalent to 458.94 kilonewton. So these are the tension at cable A and along point B. So we've got all the necessary reactions. So I think we are done here. So that's it for the parabolic curve carrying a distributed load. So this just an application of joint method as well as components. Okay, so please stand by for another example. So thank you and God bless.